Okay, welcome to the lesson on Newton's first law. This topic is rather challenging to understand. It's a simple concept, but it's challenging to understand. So try to pay close attention and follow along. This is going to be one of the more lengthier videos just because this concept requires a bit of depth and explanation. So Newton's first law. Isaac Newton was a 17th century scientist who put forth a variety of laws that explain why objects move or don't move as they do. He had three laws of motion that became known as Newton's three laws of motion. The focus of this lesson is Newton's first law of motion, sometimes referred to as the law of inertia. This is going to be a key word, inertia, so we'll talk more about that later. Newton's first law of motion is often stated as an object at rest stays at rest and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So this chart summarizes his law rather nicely. So Newton's first law applies to any object that has forces on it that are balanced. And basically what this diagram shows is there's two scenarios that can occur if the forces on an object are balanced. If the object is at rest, in other words, if it's not moving, it will stay at rest. It will stay unmoving. And that is pretty simple to understand because we experience that every day. Most people, when they see a stationary object, they see that it's not going to move unless there's some kind of a push or pull on it that makes it move. It's going to stay stationary. So that one's an obvious one. The second one, objects in motion that have forces that are balanced will stay in motion. This one is not so simple to understand because most objects that are moving tend to come to a stop when we see them on Earth. And it's only when there's a frictional force or a gravitational force acting on an object that makes it change direction and stop. But if the forces were actually balanced on an object, it would continue moving in a straight line path in forever at constant speed. So we'll talk more about that in just a moment. So example one, a book is sitting at rest on a table. Okay, so we learned about drawing free body diagrams. So if a book is sitting on a table and it's at rest, then the forces on it are balanced. There's a force of gravity acting down and a force normal acting up. So the forces are balanced. That means the object is at rest and it's going to stay at rest unless an unbalanced force moves it or pushes it vertically or horizontally. So it's going to sit there. It's going to stay the way it is. That's pretty simple. That's Newton's first law. Okay, example two, a baseball is thrown forward and travels at constant speed. So now this law is not so straightforward. So let's imagine a baseball thrown on a field somewhere. When the baseball is thrown, there's a force acting forward while the person is touching the baseball. But once it's let go, there is no forward force. The object moves forward because of Newton's first law. The object moves forward because it's in motion and it wants to stay in motion. So it's moving forward even though there is no forward force. The object, the baseball, gets pushed towards the ground, and once it hits the ground, there's a gravitational force on it, there's a normal force, and there's a frictional force. The frictional force maybe the grass on the field slows the baseball down and it stops. So that is what we normally notice. However, if we got rid of friction on the ground and got rid of gravity and we threw the baseball in space, let's say somewhere really far away from Earth or any other planets or stars, and there was no gravitational force, if imagine a person throws the baseball would have a force on it while the person's throwing it, but once you let it go, there's no forward force, just like on Earth if you threw the baseball, and there's no force of gravity or friction, so the baseball would have no forces on it, and the forces on it are balanced, but the baseball would continue moving in a straight line path at constant speed forever. Okay, so this is what is really difficult to understand because we don't experience that on Earth because there's always some friction somewhere. But if we got rid of friction and we just imagined a baseball being thrown in space, you threw the baseball, it would move forward at constant speed in a straight line path forever. That's Newton's first law. So the book explains the first part of the law. If something's at rest, it stays at rest. The baseball explains the second part of the law. If you toss a baseball forward, it'll move in a straight line path forever if the forces on it are balanced. Now, the closest thing we come to on Earth are things like a hockey puck on ice. So, for example, when you, let's say a hockey player slaps a puck, it moves forward. When it's hit by the stick, there's a forward force, but once it's moving, there's no more forward force. It moves forward because it has a tendency to want to keep moving in a straight line path. And that's Newton's first law. So there's a force acting upward of the ground pushing up. There's a force of gravity acting downward. And there's a very small force of friction acting opposite the direction of motion. If this force is really small, so the puck slides on the ice for a very long time and it continues moving in a straight line path at a constant speed, and it would keep going forever. If we got rid of this force completely, it would just keep moving forever. That's Newton's first law. Okay, everyday examples of Newton's first law. If a person is driving in a car and suddenly hit the brakes, the driver will continue to move in the direction of the car. A seatbelt is used to apply a resistive force to the person to stop them from moving forward. So guy's driving, car stops, but the guy keeps moving forward. That's Newton's first law. Once you're in motion, you want to keep staying in motion. There are many more applications of Newton's first law of motion. Blood rushes from your head to your feet while quickly stopping when riding a descending elevator. So when you get up, for example, really quickly from your seat, the blood is stationary and it's lower it's near the ground because you're seated. And when you stand up quickly, the blood does not want to move right away. It wants to stay stationary, and so you get dizzy or you faint. The head of a hammer can be tightened onto the wooden handle by banging the bottom of the handle against a hard surface. So if you bang the bottom of the handle against a surface, the top of the hammer, the head of the hammer continues moving downward even though you stop the handle from moving. To dislodge ketchup from the bottom of a ketchup bottle, it is often turned upside down and thrusted downward at high speeds and then abruptly halted. Headrests are placed in cars to prevent whiplash injuries during rear-end collisions. While riding a skateboard, you fly forward off the board when hitting a curb, a rock, or other object that abruptly halts the motion of the skateboard. These are all examples of Newton's first law. It's either saying an object is staying at rest and wants to stay at rest, or an object is already in motion and wants to keep moving. This tendency to resist changes in their state of motion is called inertia. Another word for Newton's first law is the law of inertia. Inertia is the resistance an object has to its change in its state of motion. So one of the ways to think about inertia is a grocery cart full of groceries. If you're moving a cart full of groceries, it's really hard to get it to start moving. But once it's moving, it's really hard to get it to stop moving. So something with a lot of mass wants to resist a change in its state of motion. If it's standing still, something with a lot of mass is going to want to stay standing still. If it's moving, then it's going to want to keep moving. And imagine an unfilled grocery cart. A lighter object is easier to start moving and easier to stop moving. So inertia is directly related to mass. Prior to Newton, most people thought it was a natural tendency for objects in motion to come to rest. If that was the case, the universe would not be expanding. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across a table and watch it slide to a rest position. The book in motion on the tabletop does not come to a rest position because of the absence of a force. Rather, it is the presence of a force, that force being friction, that brings the book to a rest position. So if you slide a book across a table, it's not the fact that there's no force pushing it forward once you let it go that stops the book. It's that there is an unbalanced force, friction, which causes the book to slow down. Even today, people still believe that a force is required to keep an object moving. All objects resist changes in their state of motion. All objects have this tendency. They have inertia. But do some objects have more of a tendency to resist changes than others? Yes. We already talked about the grocery cart example, which describes inertia and how mass affects it. Okay, and that concludes our presentation.